So we begin our colloquium for today. So it's a pleasure to have Soumendra Dhanee as our speaker, and he's currently a chief scientist at VJT Inc. And he's one of the big players in deep learning. So over to you, Soumendra. And I've known Soumendra for many years. He was my batchmate at CMI, and it's really endearing to have him.
Right. Thank you, Agnit. Those were very kind words. All right. So I'll just talk a bit about myself before going ahead. So currently, I'm the chief scientist deep learning at VJT Inc, where I work on computer vision problems. I've been working on machine learning problems and deep learning, particularly in computer vision, close to a decade now. And you can find me as Data Biryani on Twitter. And talking about a few things I've helped build over the years. So I've built adaptive test-taking platforms, which basically use traditional tabular machine learning, job recommender system, a hybrid of tabular machine learning plus NLP plus deep learning. Looking at computer vision problems, I have built brain volumetric segmentation model. So you take the scan of a 3D scan of a brain, and you use a deep learning model to segment various parts of the brain and measure their volume. Currently, I am building an automatic defect recognition system for high energy X-ray images. So these are the kind of systems you need for scanning, let's say the kind of motors that go into missiles or rockets or car engines. So those kind of high energy X-ray images. The task is to automatically identify defects using deep learning. I have also built image search and recommendation engine in the e-commerce space, where you take an image and find other images which are semantically similar to the given image. So by semantically, we mean the right context, right? So you just don't want to find another t-shirt given a t-shirt, but you want to understand the style, the fashion sense of the t-shirt and find something that is similar to it. So you do the search and do recommendation based on that. So I know I called this deep learning today and tomorrow, but any conversation about deep learning today is will be incomplete without talking about how we arrived at here. So we'll look at how we arrived where we are right now, and the kind of things that we can do with deep learning today, and where the space is going next. So my expertise is mostly in the computer vision area, so I'll not be able to provide any insights in natural language processing as such, but that's what we will do. And lastly, I'll talk about how do we go about exploring this. So if you want to check out things, understand the models, build one yourself, how do you go about learning and exploring? And I'll also share like what do I do as part of my job, the kind of things that I do to build models and solutions. Right. So let's look at it. So deep learning is all the hype right now. And as a mathematics department yourself, I'm sure a lot of you are looking into deep learning right now as well. Because deep learning models have been fairly successful, spectacularly successful, I would say, at a lot of problems, including solving mathematics problems. So here is the traditional timeline. We will not go spend a lot of time on it. But 2012 is basically when the AlexNet model came out. So here, this dropout mention that you see attributed to Hinton, that comes from the AlexNet paper, which demonstrated for the first time that a deep learning model could actually do very well at human perception tasks. So when we talk about machine learning versus deep learning, technically speaking, theoretically, they're kind of the same thing, except for different kind of architectures, different kind of techniques. The crucial difference is this. When we talk about machine learning, we talk about problems where we have very few number of features. So your typical data set that you will find probably has around 100 or at best thousands of features. At thousands of features, you're looking at a really, really large machine learning data set. On the other hand, tasks related to human perception, like computer vision or natural language processing or audio processing, typically they have millions of features. For example, in computer vision, if you look at the typical HD image, the high definition image, so every pixel is a feature. So if you look at it, it has close to 1.9 million pixels. So you have 1.9 times 3 number of number of features, because they're represented as an RGB space, red, green, blue. So you have 3 numbers for each pixel. So you get like 5.4 million features. And doing well in the presence of such a large number of pixels, where each feature is not very meaningful, that was outside the purview of outside of the effectiveness of traditional machine learning models. So which is what deep learning models made possible. Excuse me. So the key moment came in 2012 when AlexNet was released. And looking at AlexNet, you can understand how the field is progressing today. So we already had CNNs. CNN is a specific kind of architecture that has proven to be very successful. So we had CNNs theoretically since the late 1980s. We had backpropagation algorithms as well, which are used to train these models, right? But the breakthrough really did not happen till 2012, because because 3 key things happened in 2012. So we got really a lot more data to train our models on. That came from a data set called ImageNet. Fei Li was the lead investigator on that. We got more compute. So basically, we could take our scientific computations to graphics cards, which was later formalized with libraries like CUDA. And lastly, regularization. So deep learnings had a really bad reputation for overfitting on their data sets, and dropout methods like dropout made a huge difference to that and made a paper like AlexNet possible. So these 3 things still remain an integral part of how we build our deep learning models. So now we have moved beyond CNNs, but no matter what architecture you look at, more data, more compute, and regularization, the right kind of it, still remains critical to building a successful deep learning model. So in fact, when you look at AlexNet, this is the architecture diagram of that, and you see there are 2 parallel lines. There's a top line and there's a bottom flow, right? So the thing is, the GPUs were not very powerful back then, and they had to split the image into 2 different parts and run it through 2 different parallel GPUs so that they could fit into the GPU memory back then. And so this was a pretty clever engineering to make the whole thing work. And that remains true even today. So the theory part remains that you have to play with master, but none of it will lead you anywhere without the engineering part of it. So it's equal parts theoretical expertise and equal parts engineering expertise to make deep learning work. And most importantly, another thing that happened with the AlexNet paper. So if you read the AlexNet paper, so you'll see a lot of interesting ideas mentioned there. So one of the other key thing that happened was that they empirically demonstrated a specific kind of technique working, mainly ReLU. So till that point of time, if you looked at any deep learning model, they typically used sigmoid or tanh activations. So you might have heard the term, right? Deep learnings are non-linear learners, right? They can learn the non-linearity in the data. That comes from these activation functions. So everyone used sigmoid or tanh because they were nice mathematically as well. In the AlexNet paper, they used ReLU though. And the thing is, it is not really nice as sigmoid or tanh. It's not differentiable at this point, right? So sigmoid and tanh you might have come across already. So if you look at ReLU, it's basically max of 0 and x. So x equal to x when x is positive and x is 0 when it is negative. All right. And the thing is, there is no mathematical justification for this. So there isn't any, specific proof that ReLU is going to work well in practice. So the only thing is that it solves a specific kind of problem. If you look at sigmoid and tanh, they basically saturate at 1. The values cannot go beyond 1, right? So no matter how large or how small x gets, you cannot get a value more than 1 or less than -1. So, right. So while they are good functions to catch nonlinearity in the data, in practice, they pose a lot of problems, right? And so they just thought, like, why not just suppress one part and then take x equal to x for all the positive numbers. So this is a nonlinear function introducing nonlinearity in the models, right? And there was no mathematical reason why this would have worked better. They simply tried and it worked better, significantly better. And that since then, you can say this has been one of the grand traditions in deep learning, which is that the practice takes a precedence over theory. So if you cannot always predict in advance if a particular mathematical technique is going to work better or not, there will often be two different kind of arguments. One arguing that this will work better, another one saying that intuitively, this will not work out very well. The only way to settle it is to just work out and just try it in practice and see if it works better. Right. So, so basically, you suppress all the negative gradients flowing through your network. Right. And once these basic ideas were in place, we had an explosion of ideas. Like people demonstrated that. So first of all, when AlexNet came out, it demonstrated its superiority compared to other traditional computer vision ideas. And within a couple of years, all the traditional CV ideas were abandoned in favor of deep learning. And a lot of different techniques and applications came along. ResNet was notable because the original task of image classification for which AlexNet was trained. With ResNet, we actually exceeded what human beings could do. We matched and then exceeded human capacity for image classification in the ImageNet data set. But other than that, we have made progress in a lot of different directions. Transfer learning was critical because, as it turns out, we can train a model on a very large data set and then take that model and retrain with a different kind of task altogether. So the same model that was trained for image classification, you can take it and retrain it, fine-tune it for image classification on a smaller data set, or you could take it and do object detection or some kind of semantic or instance segmentation. So you could transfer the learning that was embedded inside the model. That was one big reason for why deep learning became so popular, because once these large pre-trained models were there, you could take them and apply them to your small task that you had. So we had, so we started with Dropout, but we improved how deep learning models were trained. Adam was a Adam mix up. So these are all different techniques that we use in training deep learning models. Neural style transfer. So as we figured out, the reason why transfer learning was possible was because deep learning was learning the concepts in a hierarchy. So we could basically take the concepts that has been learned in a specific layer of a deep learning model, and we could use that to transfer the style of one image to another. And so the creative application of which was basically we could create new images that look like popular paintings. We also figured out how to make the deep learning models really, really small. MobileNet was a notable model for that. So very small model that could fit inside a very small device, which reproduced most of the performance of a state-of-the-art deep learning model. So all these, so what I've described so far happened in the computer vision space, but we also had improvements in sequence modeling with RNN and LSTM, those kind of architectures. So if you look at an image is basically a two-dimensional structure, right? Every pixel inside an image has some relationship with the pixels around it in the two-dimensional sense. So, but we also want to do sequence modeling, for example, language. So when we look at a piece of text, every word has a relationship with the words that came before it or that came after it. So that's what we call sequence modeling. So which is applicable to natural language, audio, and time series data sets, those kind of things. Later on, we also figured out how to generate images, how to basically capture the essence of an image. When I talked about an HD image before earlier, so with its 1.9 million features, how do we reduce those 1.9 million numbers to maybe 1,000 numbers and then reconstruct that entire image back? So there were a few ideas around that space, and GANs were particularly successful, where we played two different networks against each other. One network specializing in finding fake images, and one network specializing in creating realistic fakes. And once they trained well, the faker network could generate very realistic looking images. So that was all the race a while back, if you remember. And then we got transformers, another architecture which was really good at doing sequence modeling, which we were later able to transfer to training image models as well. Lastly, reinforcement learning. So there had been a lot of breakthrough that you might have heard of. We finally built AI models which could defeat the best human players in chess or Go or do protein folding. And across all the tasks, classification, detection, segmentation, generation. So for each kind of modality, computer vision or natural language or audio, we made a lot of breakthroughs. So we were far from being perfect, but we got pretty close. All right. So before I go ahead and talk about where we are now, so let me give you quickly give you a very small example of how CNNs work, so that you have an intuitive understanding of how these models are built, how do we think about them. So when you really get down to it, if you look beyond all the mathematics, the basic idea behind most of these models are fairly intuitive and they make sense. Again, there is no mathematical reason why this would work as well as it does in practice, but the ideas are fairly intuitive. So this is what your typical artificial neural network looks like. You get some data through the input, and you combine them, and make them pass through an activation function. So data comes in, gets transformed, and finally in the output layer, you make it predict something. That's how the typical ANN goes. And if you look at the modern CNNs, so which constitutes of a large part of the modern deep learning models, the idea is essentially similar, and most of the architectures are similar as well. You get your input, which has basically a lot of pixels, and those are the input, and you make them pass through some CNN layers, and at the end of it, so these are all, so think of them as some two-dimensional structures. I will explain that in a bit. So you take the input, you again pass them through these CNN blocks, and by the end of it, you flatten them. These were two-dimensional structures. You flatten them, and it again starts looking like your typical ANN. So all these linear layers that you see here, these things at the end are basically the same idea. So you take the ANN and you put the CNN inside it, and this CNN block basically learns the geometric properties of the images, and we to create features that we then use to do our machine learning task. So, and so let's look at CNNs in brief. So, like, why do they work well? So let's first understand what we are trying to do when we try to do trying to do some kind of image processing. Let's say this is our original image. Our holy grail is to find this image, no matter how it is transformed in other images, right? So this image, for example, could have been translated, or this could have been scaled down or scaled up, or it might have been rotated, right? So these are examples of 3 transformations that would happen to images inside uh, uh, inside an image, right? So what we want to be able to do is build a model which takes this image and finds it, understands what it looks like, and it finds it inside another image, no matter how it appears there, right? So this is the object, and we want its identity to be invariant, irrespective of these transformations. Say it goes through this transformation, which is translation here, but we still want to be able to say that this object and this object, they have the same identity. And similarly, irrespective of scale, we want to be able to say that all these 3 different objects appearing inside this image, they all have the same identity. So we want to achieve this object identity invariance, right? And how do the CNNs do that? The CNNs don't really do that. They are not invariant to all of these different transformations. They are invariant against only one kind of transformation, which is translation. And that's literally how CNNs are built. So there are a lot of different perspectives to looking at a deep learning network like CNN. So I will borrow one from digital signal processing, and I will explain it in terms of that. So the basic idea is that we want to find this image, right? So we simply take this image and we literally scan across the entire photograph. So we take a small patch here, small patch here, small patch here. So we split the entire image into grids, and we take this image and we then compute which of these cells in this grid are similar to this, similar to the one similar to the one image that we want to find. And we know the answer to that, right? How to compute which of these grids appears similar to this image. And that answer is correlation. We simply calculate correlation. So we take this image, we slide it across the entire image, and we see which patch resembles the most to the given image that we have. And that's it really. I mean, so what I've described is essentially equivalent to the convolution operation. And that's what we do. So we take an image. This is what we call a kernel. And in real life, it doesn't look so well formed. We look at very small sized kernels. So we take those kernels and we simply identify which part of the image looks very similar to my kernel. And we essentially do that a few times, and those are our features. The signal that this part of the image or this part of the image, or in this image, for example, this part of the image will look very similar to my kernel. So those are the signals I simply pass on, and at the end of it, we can use ANNs or any other machine learning model to build an AI model, a deep learning model, which will tell me that in this image, this is the part where I will find my object. Excuse me. Right. So given this, you would expect that there is no scale or rotation invariance really. And here is a very small example of this. So let's say I want to find out if this box has an X written in it. And instead of taking an image of an X and comparing it with all the entire image, which is what I seem to be doing earlier, what we do is we take very small size kernels. So instead of trying to find the entire X, I will try to find if this image contains this part or this part, the center part, which is this kernel up there, or this part, the kernel up there. So instead of trying to find if patches of the image correspond to my kernels, I will simply take very small parts which capture some kind of pattern, and I will see if they appear in the image, how often, and I will simply build out model on top of that. So these are my signals. These are my features. The kernels are also referred to as features. So, and I will compute that and use that in combine that information to build a model. So, and that model could be anything. You can build a support vector machine on top of it, or you can use an ANN on top of it. So, any of those things will mostly work. Right. So, translation is basically the only thing that really CNNs are designed for. But when we look at other kind of invariances, they kind of get baked in with small techniques that we use. For example, rotational invariance, right? So if it is rotated by a very large amount, our CNN models will not do well against those, right? So we use something called max pooling. So if there is a small rotation, the model will be able to identify that. So that's an example of a small technique that we use to adopt other kind of invariances. And so we use a bunch of those things. So there is also the data augmentation. For example, if our data set does not have any 90-degree rotated map of India, we'll simply generate a bunch of those. Every time a map of India appears, we'll take that as an input. We will also rotate it by 90 degrees and take that as an input. So that is augmentation. So our model now is also kind of somewhat robust against rotation as well, right? So we put all of this together, and we have a CNN which does spectacularly well at image processing tasks, right? So if you look at each of these different model architectures, each of them has a core idea why this is supposed to work. And we basically run with the idea, and as it turns out, after we get the engineering right, after we get the data right and the training right, we quite often, they work very well in practice. And if you are exploring these deep learning models on your own, that's something you should keep an eye out for. If you look at the papers directly, the mathematics of it can get quite confusing. So do read up around it. I mean, is the mathematics even correct? Some of the landmark papers that came out, as it turns out, the mathematical reasoning they gave for why this should work turned out to be wrong, except that they work very well in practice. So that's something to keep in mind, right? So now let's look at where we are today, the kind of things that we are doing well with. So I'm just going to talk about a few applications, just point out a few applications. You probably have mostly heard about it already. So I'll just go through it quickly and then point out the basic structures that power these, right? GPT-3, all of you have probably heard about, right? Just like ImageNet, which is basically a very large data set, made models like AlexNet and its successes to be possible. We similarly had really large data. People simply created really large data sets and trained these models on it. So GPT-3, GPT-Neo, GPT-J, lots of different variants of that architecture. We also have models like OpenAI Codex, which is essentially the same architecture, but built for coding autocomplete kind of tasks. You write half the code and rest of the code is auto-generated by the model. Image generation is another thing that we did really better at right now. So if you remember neural style transfer that I talked about earlier, so that's what, so if you look at the images in the top row, these are the kind of things you could do with neural style transfer. You take the style of the source image, the Starry Night by Van Gogh here on the left, and you could apply it to a photograph of Taj Mahal on the right. Right. So the thing is that you had no control over how it got applied. And except for a few curated examples, it didn't really work all that well in practice. But now with the modern image generation architecture we have, if you looked at DALL-E or DALL-E 2 or Stable Diffusion, so that's all there is these days. So this is the kind of image that is now made possible. If you look at this image, The key thing about it is two. First of all, we did not simply give an image and ask this style to be applied to it. We actually would typically give a textual prompt describing the image. So even if this image did not exist in reality, we could simply describe this image: a man standing on a mountain looking at mountains and a starry sky, uh, 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 in the style of Van Gogh or something like that. And it would create this entire image. And most notably, you could have different styles appropriately applied to this image. So if you basically look at the bottom part of the image, this is in a style that is different from the sky, and this is more realistic, right? This is what you'd expect it to look like. So it's not, so basically it can take our prompt, our text, our instruction, and generate an image accordingly. Right, and to demonstrate it, here is what real life examples look like. So these examples are taken from lexica.art. So this is what a typical prompt looks like, and this is the generated input. As you can see, we can be very, very specific about the kind of image that we want to generate. So this is another example of a small video that is generated from a single photograph. So if you look at this video, this was not an actual video. So this is a single photograph, but we could extract a depth map and create a small video around it. So you can explore NERF and related models to see more of those. And a lot of similar exciting applications, right? We can interpolate frames between videos. We can transfer motion, like we can transfer the dance moves of a movie star from one video and apply it to another person in another video. We can do high fidelity speech transcription. That's the Whisper model that came out recently. Self-driving vehicles and a text prompt to image, video depth map, those kind of things we can do. We can do semantic search. When we search for a query, we can ask it, we can expect the semantic context to be taken care of. So a lot of different applications that is out there. But what really powers these things? And that's the thing I'm covering on in the tomorrow part of this presentation. So the key things that make these things possible, and where you can expect more and more fancy mathematics to be applied. So nobody really talks about these things, but let me take a moment to talk about a few of these. So transfer learning we talked about earlier. That is really the bedrock of all of these applications. I mean, very few people can afford the kind of infrastructure that Google or Facebook has. But since these pre-training models are open sourced, and some people have started calling these foundation models, we can take these models and fine tune them to whatever task that we have at hand. And we are going to need an order of magnitude lesser amount of data to do those things. So this is critical to how we move forward. And in fact, stable diffusion, if you have heard about it, this is the cornerstone of their strategy. They want to take all these really large models and create them and release them in the open space. Right. And here is what I think going to really make a difference for the next 3 to 5 years in our deep learning journey: multimodal foundation models. So this is something that people don't talk about a lot, but this is something I have followed closely. There was a paper called Device that came out quite a while back, and I was really excited about what that paper could do. Essentially, you embed text and images in the same space, right? So if you essentially look at all deep learning models, the fundamental thing that we are doing is we are taking a really highly dimensional artifact like an image or a piece of text, and we are translating that to very few numbers that correctly capture the information that is embedded in that image or text. And that set of numbers now we can use for all sorts of applications. We can do classification or detection. We can generate new images or new text. But for all of those applications, those few numbers, those are the critical ones. And you can actually look at the entire field of deep learning as essentially trying to do that. Take a complex artifact with millions of dimensions and reduce it to a few numbers in some kind of embedding space. And this literally is, the most important applications of everything that you looked at. When we looked at GPT in an earlier example, for example, right? So if you look at GPT's API, they expose that underlying embedding too, if you want to use that. And if you are going to use, if you are going to build something that is not satisfied by GPT's use cases, you would need those embeddings. You can simply put your text in, get the embeddings back, and build your machine learning or deep learning application on top of those embeddings. And if you look at DALI or Stable Diffusion, for example, there too, the most critical model there is CLIP, which basically what you're looking at right now in this image. So it has an image encoder and a text encoder. And the important thing is that no matter what you provide it, either an image or a piece of text, both of them get embedded. So it can give an embedding for both of them in the same space. So, you take two different points in that space. The point could either be an image or it could be a piece of text. So given a piece of text, you can find the images that are very close to that text, for example. So this kind of multimodal embedding models, so these are going to increasingly power more and more applications. If you look at Stable Diffusion 2.0, for example, which came out earlier this week, they essentially trained in open source version of CLIP, which was earlier a closed source model by OpenAI. So this is where a lot of work is going to go. And lastly speaking, I'm not going to go deep into transformers because they tend to be a bit complicated as an architecture, and it'll be too detail oriented. But I expect, again, if you're looking at the next 3 to 5 years of timeline, transformers you can expect them to be one of the best performing model architectures out there. So sequence to sequence modeling, they've already pretty much wiped the floor with everything else out there. They have also started making inroads into computer vision tasks, and a lot of the top models right now you will see use transformers architecture. So this is something you should certainly keep in mind. Right. So now I'll just take a few minutes and I'll talk about two things. How do you go about exploring the entire space? How do you discover things, ideas on your own? And how do you increase your expertise in the domain? And I'll also talk about how I do those things. Excuse me. Right. So you already have mastered the theory, or you are going to. And right. So if you are going to get deeper into deep learning, you essentially have to master the engineering parts. For that, you're going to need 4 things. These are the 4 things where you should focus your attention and efforts. You're going to need a deep learning library. You have to explore and learn. So we talk about the deep learning fire hose. The number of papers that are coming out every day has simply exploded. And you do need to be systematic about how you go about exploring these things. You are going to need a lot of practice and you are going to need a lot of compute. So we cannot really ignore the last one. So you might be ready to put in the time and effort, but you also need to figure out how to get a lot of compute to do your practice. So the first thing we look at is deep learning library, right? So generally speaking, the initial choice of framework will not really make that much of a difference. You master one framework, you will be able to take your learnings into another framework and master it quickly. But the point of this entire section is to give you quick pointers, choices with which you can't go wrong right now. And that answer would be PyTorch. So given you are coming from mostly academic background, so if you simply look at the fraction of papers using PyTorch and versus TensorFlow right now, you can simply see the explosion that has happened in PyTorch. And there's a lot more support for the kind of things you would want to do, etc. So my recommendation would be go ahead with PyTorch. But having said that, do not start with PyTorch right away. I would recommend go with FastAI. So it's a library written on top of PyTorch. So you can look at their website. You can check out the free courses that they have, which are pretty good. FastAI itself is a library, and this is the docs page. And lastly, they also have a library for using Jupyter notebooks to write your code. So the last one might not make a lot of sense if you haven't written any code for deep learning. Pretty much all of which is written in Python, by the way, just to mention that. So if you are going to deep learning right now, expect to write a lot of code in Python. And NVDev basically powers one way of writing code in Python and is fairly intuitive. And that is something I would recommend using. They also have a book, so you can also take this book and get started with it. So FastAI is a pretty good way of getting started. The thing is, it does not stop you from doing more complicated things. A lot of FastAI parts, you can simply swap them with native PyTorch components, and the whole thing will work. So the way you should look at the whole thing is that you need to write a machine learning or deep learning training loop. And for the training loop, you need a bunch of components. All these libraries, they will give you nice training loops, but which you can entirely ignore and write your own training loop as well. And all those components you can write with PyTorch anyway, so that's not a big problem. So what do I use at work? I don't use FastAI though. The very specific kind of computer vision problems that I work on, FastAI does not have very good support from them out of the box. So that is not something I can use. So I use PyTorch as a meta library on top of PyTorch. I use PyTorch Lightning. So so you'll find there are a lot of different libraries to accomplish various tasks in deep learning. So I use a few packages from something called OpenMM Lab. So, starting with PyTorch is kind of okay, but if you want to do classification, detection, or segmentation, you should typically be using something higher level. So I use those 3 packages from OpenMM Lab. I use Detect-on-2 for the same things. To understand the models that I have built, I use Captum. ANOPS is a smarter way of writing layers in a deep learning model. Scikit-learn is a generic machine learning library that has some useful components. XGBoost is very good for tabular machine learning models. And Transformers is basically, I talked about those Transformers architectures earlier, right? So Transformers is a library from Hugging Face, which is pretty useful. To understand my data set, I use 51, CVAT for data annotation, and 1B for logging the outputs from my model. So, and if you look at any professional setup, it will have a large intersection with these packages or something similar to these. You will need something to interpret your models. You'll need something to explore your data set. You'll need something to annotate your data, to monitor your experiments. So this is just one example that works for me. If you are looking at production use cases, if you make the transition to a role in the industry, you can expect to work with Docker. Streamlit is a package to build dashboards by pure Python code. You don't need JavaScript or HTML or any of those things to build a dashboard. You can simply do that with Streamlit. Pydantic is so if you have any background in Python, I would recommend you use the Pydantic library to write your classes, and check out a book called Robust Python, which is basically how we write modern Python code with a lot of type hints and yeah. So get good with type hints. This is what these are just a few things that you need in a more of a production setup, which is part of my job. Right. How do you explore and learn though? So if you just create a Twitter account and subscribe a few accounts and get a lot of you'll get a lot of recommendations for a lot of papers, and you have no way of knowing which one is good, or does this one matter at all. So there is one rule of thumb that you should follow, which is that do not look at a paper which does not have the corresponding code, or at least a promise to do that. So you'll find that so I'll emphasize that point again, which is that the engineering part of it is really, really important. And quite often you'll find that, you look at the paper, it says one thing, but when you look at the code base, they're actually doing a different thing. And the different thing which they have not even talked about in the paper is what it is the thing that makes it work. Right. So those kind of surprises can be there, particularly when you're looking at state of the art. Right. So that I think is a rule of thumb that you can follow, which is that do not look at a paper that does not have the code or data set available with it. So we have really good availability of code and data sets. It has become the standard practice in the industry and in academia as well. So if something does not follow it, you probably will be better off not looking at it. Though as academicians, you might have to again. I mean, the rest is up to you. That's my rule of thumb. And one place I really go to is papers with code. So every time I have to, let's say, look at a new task, I simply can go to papers with code. I will look at the task, and that page will typically have one small description of the task. And most importantly, it will have the benchmark on different data sets. So if you look at in this column, so for these different data sets, they will tell you what the best papers are. They will have a link to the paper, and most importantly, they will have a link to the code. And if you expand on a specific data set, it will tell you, it will give you all the top papers in that particular data set and their code and their performance. And you can explore all of that looking at these links on the side as well. And this has been really very, very useful. So, you know, when you're starting to explore, you might find that you may feel like you want to explore a large area, you know, go breadth first rather than depth first. My recommendation would be go depth first. Take a task, understand that task well, understand what is happening in that task. Of course, if you don't have any background, jumping into it directly would be probably counterproductive. But once you have a basic lay of the land, you should go deeper into tasks one by one. And that's going to build up your deep learning muscle better than just taking an overview of the entire field. So papers with code is excellent for that. They have data sets, tasks, subtasks, and different deep learning techniques. You'll find that it's the best place to explore deep learning today. You will also find that Hugging Face. So another thing that you'd want to find are a lot of models and data sets. All right, all those papers are there, but you need data sets to play with. You need models, pre-trained models to train those on. So simply go to Hugging Face and they will give you all the data sets and all the models that you need. It's a very good resources for that. And they're also trying to, I think, catch up with papers with code as well. So they are also putting out a lot of courses and exploration of different tasks. So they're adding those things also. So that is another good place to generally explore the whole area. And lastly, there are a lot of AI-based tools which will explain a paper. Like, since you will be new, there could be things that you could miss out on a paper, not understand what it is talking about. You can simply go to one of these solutions. Explain paper, for example, will help you understand your paper. There are other tools where it will implement the papers paragraph by paragraph, which is really great when you are starting out. So you can use a bunch of those tools. Moving to the next part, lots of practice. So Kaggle is a great place to do that. It has a lot of data sets, it has a lot of competitions, and you can learn a lot by looking at your peers. A lot of people share a lot of working code in Kaggle. And honestly, if you really wanted to get started, have fun, if you do not have a research agenda in mind, you just want to understand get an understanding of the entire field, the fastest way to do that would be to get into Kaggle. So they give you competitions, data sets, a lot of code from your peers where they explain what they're doing. And lastly, free compute. I'll get on that point later on. Kaggle is important also because of the compute. Lots of practice, right? Implement papers. There will be a bunch of hackathons where they implement papers. So getting into one of those would be good. They will give you some free compute also. You can read code bases. Couple of recommendations there. Spacey.io, I think, is pretty well written code base of Python code. They do NLP, and any paper you are reading, just look at the repositories and read through that code. That's all I would say about that. That's something I do quite a bit myself. And lastly, compute. This is going to be the most important bottleneck. This will determine the kind of models, the kind of data sets that you can play with, right? And everybody thinks about this all the time. At least I do. So how much compute is good? The answer is as much as can you get. And should you buy a deep learning rig of your own? Probably not a good idea. So those graphics cards are fairly expensive. Upfront investment is probably not a good idea. So this is where Kaggle comes in again. Go to Kaggle. So a lot of people will have a lot of recommendations. These 5 you will find to be the most common. So I'm just going to go through them. Do not buy your own. Go to Kaggle. It is very useful. So they give you about 30 hours of GPU time every week. And for a specific instance, they even give you multiple GPUs. So they give you an instance with 2 graphics cards. So those things are very, very useful, will be very useful in your journey. Google Colab is like a last ditch effort. Their free tier is really, really slow, and it will be useful mostly for small data set. I mean, maybe your first month of experimentations can probably be done with Google Colab. Beyond that, it's not going to have a lot of power. And Lambda AI, so they also offer some really good instances, which are also pretty cheap. For $1 for $1 per hour, you can find really good instance there. But I think they have a lot of demand on the infrastructure. The last few times I have tried there, I have not been able to score a free an available instance. They are mostly hired away by people. So they are in a lot of demand. And lastly, AWS EC2, should you use cloud instances on your own? Don't do that. And don't even try. You might end up making mistakes, which will be very, very expensive. Like a small mistake the smallest of mistakes can easily cost you 40-50K a month. Ban you forever from AWS EC2, right? So what do I personally use at work? I use AWS EC2. So while it may not be a great thing for a great option for on the personal front, at work that works out well. So we have a lot more professional tooling at our disposal, which stops us from making these mistakes, which your personal AWS instance will not help you do that. So with the professional tooling that I have available, AWS EC2 is a good option. And I do have a few graphics cards in my personal machines also. So for tinkering, those are the things I use. Right. So that's the end of the session. And I hope